here the degree is 1, 1, 1, but here the degree is like 3. So 1 plus 1 plus 1 plus 3, again, 6 even number. So now you're starting to get suspicious. Well, every time you add an edge to your graph, the total number of degrees goes up by 2. Right? You're starting to get suspicious that's the case. And that's probably the beginnings of your proof. So now you sort of abandon, let's say you've abandoned the hope of trying to find a counterexample. So now you switch direction. You say, well, let's try for a proof, actually proving that it's true. So here's your, here's the beginnings of an idea, an approach to proving it. Like you might start with the simplest possible graph, which is just one edge, right? And therefore it has to have 2 nodes. By definition, that's what an edge is. So it seems to me that's the simplest possible graph, and it's the total number of degrees is obviously 2. 1, 1. So you add them, so 2. That's even. Now, if you add one more edge, so that'll mean adding another node. So if you have another node here and another edge, when you add that extra edge, you've added 2 to the count of your total number of degrees. Right? So each time you add an edge, your total count of degrees goes up by 2. Right? Now you start with 2, you're adding 2 to it, so you'll always get an even number. That's the beginning then of your proof, and then you have to write it up. So that's the idea, if you like, of your proof, the main idea, and then you have to write it up clearly, and we'll talk a bit about that. All right. Okay, so what do you do? So that gives you an idea of how to go about making a proof. But what do you do? What do you do when you get stuck? Because some proofs are very difficult, and what do you do? Well, these are just some guidelines. Remember, proving theorems is an art. There's no mechanical, just crank the handle. Oh, down here, yeah. Cranking the handle to churn out proofs mechanically. It's not as simple as that. But there are guidelines, experiences that experienced mathematicians can pass on to junior mathematicians, like professors to their PhD students, that kind of thing. Alright, so what do you do when you get stuck? Well, one thing is try something easier, like a special case of a theorem statement. For example, say some theorem statement involves an integer k. What's being said here we'll actually use in a particular kind of proof. There are various categories of proof, and this particular type you might use something called proof by induction, and we'll do that later. In fact, I think next board, but we'll mention it soonish. Right? So say your statement, your theorem statement involves a particular integer. It's true that the statement says that some property is true for all integer cases. N's a natural number. K is a natural number. Okay. Well, and you're stuck on how to prove it in general. Well, simplify it, the problem, and try proving it for a special case. For example, when k is 1. That might simplify the statement, the property a lot. And then if you can prove that, well, then try maybe for k is 2, and so on. And after a while, if you keep proving it, it's true for 1, it's true for 2, and so on, you might start seeing you may see then a pattern emerging of why it's true in each case, and then you might be able to take that pattern and put that into a proof, right? So it's not only true for k is 1, it's true for k is 2, but it's true in general for all k, for all positive integers k. Okay? So that might be one approach, and that approach gets a label. It's doing things that way for certain kinds of theorem statements, and called as a proof method called proof by induction. Don't worry about the label, we'll do it later, just jumping ahead a little bit. Okay, so if a special case that you choose doesn't work, and hard to prove, well, try a different special case, and so on. Okay, now assuming you have found a proof, like here, your idea, that your essential idea was every time you add an edge, your total, the sum of your degrees goes up by 2. That was the essential idea for your proof. So that was an example of it. So once you feel you've got the guts, the main idea for your proof, or you may have several. Your proof may be multi-parts, and you may need various steps. But once you feel you've got a proof, then you have to write it up. Okay, and what does a typical proof look like in pure math? Well, usually it's a set of statements, like a sequence of statements. 1, 2, 3, and usually a statement in that set will depend on that it'll be a logical deduction from statements earlier in that set, in the proof. And we'll do examples in a session or two of this kind of thing. This is speaking in general. Okay, so usually a proof takes the form of, it's like a sequence of statements, and each statement usually is a logical deduction from earlier statements. Okay, or statement, one or more, right? And your proof, it should be clear. It's really important. Okay, and correct, of course. You don't want some mathematician faulting your logic, because that's embarrassing. It makes you look bad. So it needs to be clear so that other people can understand it. Very important, very important. And of course, it's got to be correct. No errors, not a single error. Right? Even just one error can be. Like that massive proof I was talking about earlier for the classification of all possible simple groups. A classification just means you list out all possible cases, and then you prove that there are no other cases, that the list is complete. And so any example of a so-called finite simple group, don't worry about what it is, but any example has to be one of those in the list, right? So you've classified all possible finite simple groups. The total number of pages of proof for that classification was something like, 15,000 or something. Now, it's virtual certainty that somewhere in those proofs there will be errors. A lot of people think that's probably true, but those errors are relatively minor and probably relatively easily corrected once they're found. Finding them may be a lot more difficult. But some errors are very grave and just absolutely kill a so-called proof. So if there are errors, it's not a proof. Right? Proof means that the theorem statement has been shown to be true in all cases. So if there's an error in there somewhere, then it's not a proof. Now it may be a minor error, so the proof might be relatively easily corrected, just modified a little bit, and made valid. Alright. Now for this and a bit of the next session, some tips, some hints on theorem proving, rules of thumb, heuristics if you like, that have from experience have shown to be useful. One is, be patient. Okay? Sometimes you try to find a proof for some theorem statement, and you get stuck, and it's too difficult. I don't understand. I don't know how to begin. Which way to go? So be patient. Maybe a proof may take a lot of time. Well, you can't see it, but there's like 4 hints given. Second one I'll just mention is like come back to it. You may get stuck and you give up for a while, then you do something else. You might sleep on it the next day, and maybe your unconscious has been working on the problem and may have even come up with a solution or a suggestion that you might try. Like you have a flash, an idea, something you did not think of before the first time you tried or the second time you tried. Now, if it's a really challenging problem and you're obsessed by it, you really want to find a solution. You're strongly motivated to, let's say. So you may be working on it and working on it and working on it. So your unconscious mind is like full of the experience of your conscious experience of working on the problem. So it has a lot of data and experience from your conscious waking experience, and it can work on that while you're asleep, in dreams, even when you're awake. So get your unconscious mind working on it as well. So come back to it later, because you may have ideas that you did not have the first time. Okay, so a certain amount of persistence. Be patient and come back to it. Well, there are others, but that's next session. So I'll just go straight to the next session after I change the camera angle.